Pluto, a distant and enigmatic smaller celestial body, once classified as a planet in our solar system, has once again garnered significant attention, thanks to startling revelations from leading astrophysicists such as Neil deGrasse Tyson and Michio Kaku. Their recent disclosures suggest that Pluto, the icy world at the far reaches of our solar system, could be on a potential collision course with Neptune. But how is this even possible, and what might the consequences of such an unprecedented event be? Are we witnessing an intriguing cosmic oddity, or is there something more profound behind this looming celestial crash? Join us as we delve into the potential ramifications of a Pluto-Neptune collision. Pluto, which was demoted from its status as a planet to that of a dwarf planet, partly due to its highly unusual orbit, remains an object of great fascination and study within the astronomical community. Recently, leading researchers have pointed out the potential danger posed by Pluto's orbit, which, they claim, brings it dangerously close to Neptune's. This assertion, raised by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku, has led to growing concerns regarding the possibility of a catastrophic impact between the two planets, a collision that could have profound consequences, even for Earth. But how could such a dramatic event even be conceivable? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years for Pluto to complete just one orbit, meaning that since its discovery in 1930, it hasn't yet finished a single full revolution. However, what makes Pluto's orbit even more intriguing is its highly elliptical nature, which contrasts starkly with the nearly circular orbits of the major planets in the solar system. Furthermore, Pluto's orbit is inclined at an angle of 17 degrees to the ecliptic plane, making its path significantly steeper than the orbits of the other planets. This inclination and eccentricity make Pluto's orbit highly complex and fascinating to study. One of the most striking features of Pluto's orbit is its intersection with Neptune's orbital path. For approximately 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune does. This creates a natural question. If their orbits cross, why hasn't Pluto collided with Neptune already? The answer lies in the gravitational forces exerted by other planets in the solar system. The study of Pluto's unique orbit began shortly after its discovery. Early astronomers quickly realized that Pluto's path stood out because of its steep inclination and its elliptical shape. This raised a compelling mystery. How could Pluto's orbit actually intersect with Neptune's without causing a collision? The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. One way to understand this is through the three-body problem in space, which involves calculating the gravitational interactions between three objects, like Pluto, Neptune, and the Sun, and determining how their gravitational forces affect each other's movement. This is akin to trying to predict where they will go based on their starting positions and how they pull on one another. For Pluto, the three-body problem reveals that its orbit, Neptune's orbit, and the Sun's gravitational pull work together in a delicate balance, preventing a catastrophic collision. Key to this balance are the concepts of ASU libration and scope libration, along with the VZK oscillation, which help explain why Pluto's orbit remains stable despite the apparent chaos. ASU libration, in particular, ensures that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, preventing direct contact. Scope libration, on the other hand, refers to the vertical movement of Pluto in its orbit. This means that when Pluto comes closest to Neptune or any other large planet, it is positioned far above their orbital plane, offering an extra layer of protection from potential collisions. The VZK oscillation, named after three researchers, V, Zell, and Kai, who studied the movements of objects in space, describes the way that gravitational forces between three bodies, like Pluto, Neptune, and the Sun, affect each other. This gravitational pull influences how these bodies move through space. In Pluto's case, the VZK oscillation helps explain why its orbit appears so unusual despite its irregular path, ensuring that Pluto's orbit remains smooth over extended periods of time. This oscillation reveals that even though space may seem chaotic and unpredictable, there are underlying patterns that help maintain order. All of these factors contribute to the stability of Pluto's orbit, ensuring that it doesn't collide with Neptune or veer off course. The three-body problem plays a crucial role in understanding the behavior of these orbits and how space objects influence one another. This kind of research deepens our understanding not only of Pluto and our solar system but also of distant worlds and their stars. In the late 1980s, mathematical simulations revealed that while Pluto's orbit remains stable, it does have minor deviations due to small changes in initial conditions, which can lead to significant variations over thousands of years. These fluctuations are minor, but they suggest that Pluto's orbit is not entirely predictable in the long term. Despite this, simulations have shown that Pluto's orbit maintains a general sense of stability over time, preventing any dramatic shifts or crashes. These studies have also helped clarify the role of larger planets, such as Neptune, Jupiter, and Saturn, in stabilizing Pluto's orbit around the Sun. For example, there exists a special relationship between Pluto and Neptune, whereby for every 2 orbits Pluto completes, Neptune completes 3. This synchronization helps stabilize Pluto's path and prevent any potential collisions. However, it's not just Neptune that plays a role in stabilizing Pluto's orbit. The gravity of Jupiter and Saturn also helps maintain the balance. Simulations have shown that the gravitational influence of Jupiter alone is enough to keep Pluto on a stable path for millions of years. These gravitational forces, when combined, ensure that Pluto's orbit remains relatively consistent. Without them, the solar system could be far more chaotic. The presence of these stabilizing mechanisms is crucial to preventing collisions and maintaining the delicate order of our solar system. For Pluto, understanding its orbit is essential, especially with the growing speculation about a possible future collision with Neptune. By studying Pluto's orbital dynamics, scientists can gain valuable insights into the forces at play in our solar system and beyond. While Pluto's orbit appears irregular, it is in fact an example of how even seemingly unstable orbits can reach a state of balance through the interplay of gravitational forces and orbital mechanics. It also underscores the importance of continued observation and study of celestial phenomena, as our understanding of space and its complexities continues to evolve. The case of Pluto's orbit illustrates the strange and often unpredictable nature of celestial bodies, which makes them an ongoing subject of fascination. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is especially evident in Pluto's case. Even small changes in Pluto's position or velocity could significantly alter its long-term orbit. Computer simulations have proven to be incredibly helpful in understanding how Pluto moves through space, as they allow astronomers to model the gravitational interactions between Pluto and other celestial objects, such as Neptune. By making small adjustments in these simulations, scientists can see how even minor changes can dramatically affect the trajectory of Pluto's orbit. In the 1980s, simulations showed that while Pluto's orbit is governed by mechanisms like ASU libration and scope libration, it can still be erratic and unpredictable. A tiny variation in Pluto's starting position or speed could result in a dramatically different orbit after many years. Despite this apparent chaos, however, Pluto's orbit remains stable over immense time scales, often spanning billions of years. This suggests that while Pluto's journey around the Sun may seem chaotic, it is ultimately governed by certain patterns and rules. Predicting celestial events, especially those involving turbulent orbits like Pluto's, is a significant challenge. The inherent unpredictability of these systems makes long-term forecasts highly uncertain. While mathematical models are powerful tools for understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely on the accuracy of initial conditions, and even small errors or distortions can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the constantly changing and dynamic nature of the universe. While our understanding of space has advanced significantly, Pluto's case highlights the fact that there is still much we don't know. Studying the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It illustrates how the position and movement of each planet can have far-reaching effects on the stability and trajectory of other objects within the system. So, why are prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku raising concerns about the potential collision between Pluto and Neptune, despite all the mechanisms in place to prevent such an event? Tyson, a leading astrophysicist and a well-known figure in popularizing cosmology, provides a unique perspective on the ongoing mysteries of our solar system, particularly the curious case of Pluto. Tyson, known for his role in Pluto's reclassification from a planet to a dwarf planet, argues that the renaming was not a downgrade, but a necessary step in light of our expanding knowledge of the many bodies orbiting the Sun. His approach to celestial mechanics is one of continuous learning, recognizing that orbits like Pluto's are a sign of how much there is still to discover in space. Tyson's insights into the potential collision between Pluto and Neptune focus on the future and the long-term gravitational shifts that could eventually bring the two planets closer together. While these concerns remain speculative, they serve as a reminder of the unpredictable nature of space and the limits of our current scientific understanding. On the other hand, Michio Kaku, another influential astrophysicist, also acknowledges the chaotic dynamics of planetary orbits, though from a slightly different perspective. Kaku is renowned for his work in theoretical physics and his ability to communicate complex scientific ideas to the public. He emphasizes that while small changes in planetary orbits can have significant long-term consequences, the possibility of Pluto colliding with Neptune remains a distant concern, potentially billions of years away. Kaku stresses the importance of continued research, advocating for more advanced simulations and better technology to track the movements of distant celestial bodies. He views the potential collision not as an immediate threat, but rather as a fascinating scientific mystery to study and explore. By improving our understanding of the forces that could lead to such an event, Kaku believes we can better predict how and why such a collision might occur, or why it may ultimately be avoided. So, what would happen if Pluto and Neptune were to collide? While the scenario remains speculative, such an impact would undoubtedly be catastrophic. Both Pluto and Neptune are primarily composed of ice and rock, though Neptune is much larger, with a mass about 17 times that of Pluto. A collision of this magnitude could send shock waves throughout the outer solar system, potentially altering the orbits of other bodies in the Kuiper Belt and even impacting objects in the inner solar system. However, the likelihood of such a collision occurring in the foreseeable future remains incredibly low. The current gravitational mechanisms that stabilize Pluto's orbit continue to ensure its safety, minimizing the probability of a direct collision with Neptune. In the meantime, the study of Pluto and its interaction with Neptune provides invaluable insights into the ever-changing dynamics of our solar system. By examining the complex gravitational relationship between these distant bodies, scientists are better equipped to understand the broader forces at work in the universe. The possibility of a future collision, though remote, serves as a fascinating example of the unpredictability of space and the ongoing mystery that drives scientific inquiry. It also reminds us how much more there is to learn about the universe, as each new discovery sheds light on the nature of space, the origins of our solar system, and the potential futures that await. The work of astrophysicists like Tyson and Kaku continues to be crucial in expanding the boundaries of human knowledge. Their efforts help illuminate the mysteries of the cosmos and propel our understanding of the vast universe in which we live.